So if you recall, the simplest type of morphism that we looked at were the morphisms to A1, which exactly gave us the regular functions. And similarly for rational maps, the simplest ones of them are the rational maps to A1. And so we give them a special name. When X is an irreducible variety, we say that a rational map to A1 is called a rational function. And explicitly recalling the definition, this means a rational function is given by the choice of an open, non-empty subset of X together with a regular function on U, and a different pair U prime phi prime is equivalent if and only if the restriction to the common locus where both of them are defined is the same. And using this notion of rational functions, we can construct an important invariant of a variety, namely its function field. So if X is an irreducible variety, we just take the set of all rational functions, and then we claim that this has more structure. It has the structure of a field. And to see this, well, we need to define the operations making it a field. So if phi1 and phi2 are two rational functions defined on u1 and u2, then we can add them. And to do that, and also multiply them. And to do that, we just restrict them to the common locus where both of them are defined. This intersection is non-empty because X is irreducible. And then on there, we know we can just add them pointwise. So this is the addition and multiplication. And then there's an additive inverse because we can just take minus phi1 on the locus where it's defined. And the interesting part is it also has a multiplicative inverse. And so to see this, note that if phi is non-zero, a non-zero rational function, then it means that it must be non-zero somewhere in its domain of definition. In other words, the open set U0, which is U minus the locus where phi vanishes, is non-empty. And then on U0, we can write down phi inverse. And this is still a regular function. And so this pair here defines a rational function, and it's exactly the inverse of the rational function U phi. So here it was important that we give us this possibility of restricting to open subsets. And so we have addition, multiplication, and we have inverses to these two operations. So K is indeed a field, and it's K of X is indeed a field, and it's called the function field of X. And then some remarks. How would you compute this? The first remark is that if U inside X is a non-empty open subvariety, then the claim is that the function field of U and the function field of X agree. So the function field is an invariant which only depends on what you do on some open non-empty subset. And to see this isomorphism, well, if you have phi on here, so then this means that it is a regular function on some open subset V of U. But then the same data, of course, also gives you an element here because V is still an open subset of X. So somehow this is one direction, and the other direction is not much harder. You just start with something defined on some open subset W inside X. And then to get an element of K of U, you just restrict this to the intersection of U with W. And you can check that both compositions in this are isomorphisms, also respecting addition and multiplication. So somehow this means if you're interested in computing this function field, you can always give yourself the liberty to restrict to some open subvariety. And then using this, we can actually give a concrete recipe for computing this function field. Namely, for this, we observe one more thing which appeared in an exercise, namely that K of X is, if you go through the definition, is exactly the stalk of the sheaf O of X at the irreducible set X. So in this exercise, more generally, we had that if X is a variety and we have some irreducible subset, then we can take the stalk of the sheaf at the irreducible subset. And this was just some the sections which exist in some non-empty neighborhood of some point of this irreducible subset. And if you just write down the definition and you take the stalk at the full set X, then you exactly get the definition of K of X. And then the good thing about this is that we actually computed this when X was an affine variety, and we gave an explicit formula. And so the steps here are, let's say you want to compute K of X. Then by part A, you know you can compute it on some open subset. So what we do is we take U to be an open and affine subset of the variety X. And then K of X is equal to K of U. And K of U is the stalk of O of U at U. But this was computed in this exercise. So we know the stalk there is exactly, you take the coordinate ring of U, and then you localize, in this case, you localize at the ideal 0. And you see, this is now purely a commutative algebra, so we can compute this and then take the localization. And in fact, I mean, this is an integral domain. We localize at the 0 ideal. This is exactly the definition of the fraction field of this integral domain. And so somehow we see this is kind of a second way to see that this is indeed a field. And this is an explicit recipe which you can use to calculate it. And then the final interesting fact, which I'm not going to prove, is that this function field uniquely classifies these kind of irreducible varieties up to birational maps. So more precisely, I'm saying that there is one of these functors which starts from this category of irreducible varieties with dominant morphisms and goes to the category of finitely generated field extensions over K. And it takes the variety X and sends it to its function field. And so the claim is that this is an equivalence of categories. And so to see this, first of all, you would have to see that if you have two equivalent varieties in this category, so if X and Y are birational, then their function fields agree. But this you can check using this part A, right? If X contains an open set U and Y contains an open set V, and U and V are isomorphic, that's the classification of being birational, then K of X by this part A is equal to K of U, but U is equal to V. And then you use this in the opposite direction and see K of V is equal to K of Y. So this is a kind of well-defined, and you can check that if you have a dominant map between varieties, then this induces a map of their function fields and so on and so forth. And the interesting thing is that if you are given such a finitely generated field extension, then you can always find an irreducible variety with this function field. So if you like, you can think about this a bit. I'm not going to prove it because we're not really needing it later, but this tells us that we can, again, completely understand this geometric category in terms of commutative algebra, similar to what we have seen, that affine varieties are uniquely characterized by their coordinate rings.